We're now moving into waves. Waves transmit energy through space and time. Repeating back and forth motion about an equilibrium position is called a vibration. A disturbance that is transmitted progressively from one place to the next with no actual transport of matter is called a wave. Light and sound are both forms of energy that move through space as waves. The period of a pendulum depends only on the length of the pendulum and the acceleration of gravity, and we'll be working problems in class with that this week. A stone suspended at the end of a string is a simple pendulum. Pendulums swing back and forth with such regularity that they have long been used to control the motion of clocks. The time of a back and forth swing of a pendulum is its period. Galileo discovered that the period of a pendulum depends only on its length and its mass has no effect. Two pendulums of the same length have the same period regardless of mass. So you see this, what we have here is two masses on the end of the string, but they swing at the same period because the lengths are the same. A long pendulum has a long period and then a short pendulum. It swings back and forth more slowly, or we could say less frequently, than a short pendulum. Just as a long pendulum has a greater period, a person with long legs tends to have a slower stride than a person with short legs. Giraffes and horses run with slower steps than do short-legged animals such as hamsters and mice. So what determines the period of a pendulum? Alright, the source of all waves is something that vibrates, and that's very important to us, but we're going to talk about vibrations a lot in this unit. The back and forth vibratory motion, called oscillatory motion, of a swinging pendulum is called simple harmonic motion. It produces a sine curve, is a very good pictorial representation of this kind of motion. Frank Oppenheimer demonstrates that a pendulum swinging back and forth traces out a straight line over a stationary object and a sine curve when the surface moves at constant speed. Alright, the parts of a wave. A weight attached to a spring undergoes simple harmonic motion. A marking pen attached to the bob traces a sine curve on a sheet of paper that is moving horizontally at a constant speed. A sine curve is a pictorial representation of a wave. And if you look here, if you look at the equilibrium point that runs through the middle, if you go from here to the top of the crest or to the bottom over on this side, that's called the amplitude. The wavelength, you can look at crest to crest, that would be considered a wavelength, or you could go from trough to trough, or any two identical places on the wave would be considered a wavelength. The high points on a wave are called crests. So up here, this would be a crest and this would be a crest. The low points on the wave would be called troughs, so we would have a trough right here. The term amplitude refers to the distance from the midpoint, right here. The amplitude is the maximum displacement from the equilibrium. The wavelength of a wave is the distance from the top of one crest to the top of the next one. Equivalently, the wavelength is the distance between successive identical parts of the wave. The wavelengths of waves at the beach are measured in meters, the ripples in a pond in centimeters, or light in billionths of a meter. The number of vibrations an object makes in a unit of time is its frequency. The frequency specifies the number of back and forth vibrations in a given set of time. Usually we measure this in seconds. Frequency is measured in hertz. A complete back and forth vibration is one cycle. If a vibration occurs in 1 second, the frequency is 1 cycle per second. If two vibrations occur in 1 second, the vibration is 2 cycles per second. The frequency of the vibrating source and the frequency of the wave it produces are the same. The unit of frequency is called the hertz. A hertz of 1 cycle per second is 1 hertz. 2 cycles per second is 2 hertz, and so on. Higher frequencies are measured in kilohertz, megahertz, and gigahertz. The one way you're going to remember this, if I had hit you frequently, it's going to hertz. Electrons in the antenna of an AM radio station at 960 kilohertz vibrate 960,000 times each second, producing the 960 kilohertz radio waves. If the frequency of a vibrating object is known, its period can be calculated, and vice versa. Suppose, for example, that a pendulum makes 2 vibrations in 1 second. Its frequency is 2 hertz. The time needed to complete one vibration, that is the period of a vibration, is 1/2 of a second. As you can see, frequency and period are inverses of each other. To find the frequency, it's 1 divided by the period, or to find the period, it's 1 divided by the frequency. What is the frequency in vibrations per second of a 100 Hz wave? A 100 Hz wave vibrates 100 times every second. Again, what is the source of all waves? Alright, wave motion. The energy transferred by a wave from a vibrating source to a receiver is carried by a disturbance in a medium. We're going to talk about that a lot. Most information gets to us in some form of a wave. Sound is energy that travels to our ears in the form of a wave. Light is energy that comes to our eyes in the form of a different kind of wave. These are called electromagnetic waves. The signals that reach our radio and television sets also travel in the form of an electromagnetic wave. When energy is transferred by a wave from a vibrating source to a distant receiver, no matter is transferred between the 2 points. Think about the very simple wave produced when one end of a horizontally stretched string is shaken up and down. Each part of the string moves up and down, and the disturbance moves horizontally along the length of the string. The disturbance moves, not the parts of the string itself. Another example, drop a stone in a quiet pond and you produce a wave that moves out from the center in the expanding circle. It is the disturbance that moves, not the water. When someone speaks to you from across the room, the sound wave is a disturbance in the air that travels across the room. The air molecules themselves do not move along. The air, like the rope and the water in the previous examples, is the medium through which the energy travels. Energy is not transferred by matter moving from one place to another within the medium. The Sears Tower in Chicago sways back and forth at a frequency of about 0.1 Hertz. What is the period of the vibration? Since we said the period is 1 divided by the frequency, we can take 1 divided by 0.1, giving us 10 seconds. How does a wave transfer energy? You can calculate the speed of a wave by multiplying the wavelength by the frequency. The speed of a wave depends on the medium through which the wave moves. Whatever the medium, the speed, the wavelength, and the frequency of the waves are related. If the wavelength is 1 meter and 1 wavelength per second passes the pole, then the speed of the wave is 1 meter per second. If the wavelength is 3 meters and if 2 crests pass a stationary point each second, then the 3 meters times 2 waves passes by in 1 second. The waves therefore must move at 6 meters per second. V equals, this little x here, this looks like it didn't copy. The formula is, that's a lambda. Apparently it didn't copy across. It's the V is the wave speed, lambda is the wavelength, where F is the frequency. So don't think of it as the box, that should be the Greek letter lambda. In air, the product of wavelength and frequency is the same for every frequency of sound. That's why you don't hear the high notes in a chord before you hear the low notes. The sounds all reach you at the same time. Long wavelengths have low frequencies, and short wavelengths have high frequencies. Wavelengths and frequencies vary inversely to produce the same wave speed for all sounds. Looking at this, the wave speed that they're using is 340 meters per second. That's an average. It can change, and we'll talk more about that when we get to sound. But if you look at that, if you multiply these two numbers together, this is what you get. So all those that are multiplied together all give you 340. If a water wave vibrates up and down 2 times each second, and the distance between wave crests is 1.5 meters, what is the frequency of the wave? What is its wavelength? What is its speed? The frequency of the wave would be 2 Hertz. Its wavelength is 1.5 meters, and its wave speed would be, looking at this, the wave speed is the frequency times the wavelength, so I take 1.5 times 2 Hertz gave me 3 meters per second. What is the wavelength of a 340 Hertz sound wave when the speed of the sound in air is 340 meters per second? Well, the wavelength must be 1 meter because the wave speed is equal to 1 meter times 340 hertz equals 340 meters per second. Because if you look at it, frequency times wavelength, the speed was 340. The frequency was 340, so that means if they equal each other, this had to be 1. How do you calculate the speed of a wave? Waves in the stretched strings of musical instruments and the electromagnetic waves that make up radio waves and light waves are transverse. Suppose you create a wave along a rope by shaking the free end up and down. The motion of the rope is at right angles to the direction of the wave is moving. When the motion of the medium is at right angles to the direction in which the wave travels, this is called a transverse wave. Because if you looked through the equilibrium point here, this is creating right angles as it travels. So that makes this transverse. What are some examples of transverse waves? Sound waves are longitudinal waves. Longitudinal. Sometimes the particles of the medium move back and forth in the same direction in which the wave travels. When the particles oscillate parallel or along the direction of a wave, this is called a longitudinal wave. Both transverse and longitudinal waves can be demonstrated with a loosely coiled string. When the end of the coiled string is shaken up and down, transverse waves are made. So here we have it's going up and down, back and forth like this. This is transverse. Now if you shake it back and forth, where it's just gyrating back and forth this direction instead of this direction, these are called longitudinal waves because it's going parallel to the direction of the wave. What is an example of a longitudinal wave?